Okay, so good morning, good afternoon, good evening, depending on where you are in the world. So welcome back to this third module the third video for the first module. So in this we'll be focusing on how the environmental data is collected and basics of LCA methodology. So let's get started for next 25-30 minutes. I'll try to explain that. See, whenever we look for whenever we collect some data, you have to do some chemical analysis. So the analysis could be direct chemical measurements, could be you can use a sensor and before even you do that, you need to do some sort of sample preparation because you cannot just take a soil sample and water sample and stick into your instrument. You have to get the sample ready. So in terms of the getting the sample ready, there are some physical preparation, there could be some chemical preparation, and then you get to the analysis. Physical is mixing, drying, grinding. Chemical is your acid digestion, solvent extraction, and chemical oxidation and all that. And then you do your analysis in terms of titration, electrode instruments, and all that. So there are different types of instruments out there. They work on different principles. Where it's a common instrument that we see, there will be an increase in conductivity, there will be absorbance of light or emission of light. So those are the things which kind of is used as a tool to measure the concentration. So basically the instrument gives a response and that response correlates to the amount of sample present. Before you start any like a analysis of a sample, you prepare a calibration curve. So that's what you are looking at in this screen right now is a typical example of a calibration curve where you have given the known concentrations and you got a response and you plot a base fit line. Now you have an unknown sample. You bring the unknown sample, you get a response somewhere here. So that's a response, and you plot it. You come over here, you drop that line vertically, and you get the concentration value. So this is how you kind of measure the sample concentration. And a spectrophotometer is very common, used a lot in fact, if any environmental lab you go to, you will find a spectrophotometer. So it is used on absorbance principle, colorimetric method, which is used for which is basically the basics of these spectrophotometer methods. So when you collect the data, you have to make sure the data quality. So quality control, quality assurance in terms of blanks, spikes, replicates, blanks to make sure there is no contamination. Spike to see that you are getting your machine is running the numbers okay. Replicate is just to see that whether you're getting the same number again if the sample is the same. Any instrument has a certain detection limit. That's called the method detection limit. Is the minimum concentration that the instrument can measure with a 99% confidence that the analyte concentration is greater than zero and is determined from the analysis of a sample in the given matrix type containing the analyte. So basically, if you're running a wastewater sample after digestion and all that, you measure, you're looking for heavy metals or certain other components, the machine will always give you a number, but what number you can trust? And that says that it has to be reported with 99% confidence limit. So there is a method of doing it. You can, this is a formula for MDL. You have Tn minus 1, alpha 99% confidence, n is the number of sample, and minus 1 is the degree of freedom multiplied by the standard deviation. And so if you have a sample which you run 8 different times, say for example, if this is an arsenic concentration in a contaminated water sample, and you got all these values, you can see it varies from 12.02 to 12.57. Same sample, ran 8 times, so you find out the standard deviation is 0.19. For n is equal to 8, n minus 1 is 7, alpha 0.99, so t value is 3. So MDL is actually 0.19 times 3, which is 0.57. So what does that mean is if you get a concentration above 0.57 and above, it can be trustworthy. But if you get the concentration below 0.57, you cannot really trust that number. So you have to basically take it as a below detection. So a machine will give you a number, but that number does not really make any sense. So what will happen if your data is below detection? So when you do a statistical analysis, you need numbers. You just cannot put less than detection limit or VDL there. So how to handle it? So there are different statisticians proposes different stuff. Some says assume it to be 0. Some says assume to be the detection limit. Some suggest that assumed to be half of the detection limit, which is the most common approach taken, because some may be higher, some may be lower. So you are kind of in the middle path, and there are other rigorous statistical approaches there. So just a very quick overview of how the data is collected and what are the some basic stuff you need to take into consideration when you're collecting the data. Because for LCA, as have been mentioned earlier as well, it is the data which is very, very important. You need to have a good quality data. So now let's look at how this LCA methodology is done. Some examples to run you through in next 20 some minutes. So what does it mean to be green? I think we already kind of talked about it. What is sustainability? Let's go. So it's has to be environmental friendly, sustainable products, green products, environmental preferable, biodegradable. These are different buzzwords you keep on hearing all the time. And the sustainable development definition, as per UN World Commission of Environment and Development in 1987, when they came up with this definition, says the development meets the needs of the present without compromising the ability of future generations to meet their own needs. So that's what Brundtland Commission came up with. Our population is going up. We are consuming a lot of stuff. So we have to become more greener. So what does what the science says? Being green is trendy, but what does the science says? How can you become green? And that's what we'll start looking at the entire product life cycle, from the extraction of the raw material to the manufacturing of the primary materials, manufacturing of the products, use of the products, and then recycling, resource recovery from the product, and finally disposal. So what is the environmental footprint of the entire life cycle of any particular product? That's what we are looking at in an LCA. So in other words, it's a scientific way of looking at going green. So that's what it's all about. So it's a compilation and evaluation of all the input, outputs, and potential environmental impacts throughout its life cycle. So if you are doing a certain procedure, there has to be a certain standard. So there is an ISO standard, which is kind of helps in terms of LCA. And why you would do an LCA? Of course, you get a product environmental footprint. It's a product or project development improvement, it's strategic planning, public policy making, marketing, and eco declarations and all. So this slide is quite important. So in terms of product life cycle, what you're looking at is from the raw material acquisition, material processing, manufacture, use and service, retirement, recovery, treatment, and disposal. So this entire life cycle, you try to capture what is the material input, what is the energy input, how much is the waste has been produced, gas, liquid, and solid from different product processes and distribution. So you capture everything together as part of this LCA. So how we do it? As per ISO methodology, there are 4 broad steps. Number 1, goal and scope definition. What is goal and scope? What is the purpose of the LCA and who is the audience? What is the purpose? Why you want to do this LCA? Number 2 is inventory analysis, which is what is the function and functional unit. So what function that particular product or the service is going to provide, and what should we assign a number. For example, if you're looking at 2 different types of bulb, so function is the lights, how much light it is. The function is to provide the light. There are some secondary function, but the primary function, let's just stick with the primary function is to provide the lighting. Now functional unit will be how much units of lighting. So then what are the boundaries? Where do you stop in terms of what data do you need? I'll give you some examples and it will explain that to you, what assumptions you're making, what are the limitations. So impact assessment is as part of this inventory analysis, we collect all the material, energy input, and all the exhaust like emissions that is coming out. And then we try to see how in terms of impact assessment, how environmental, social, and economic things are getting impacted. Now, the interpretation helps you to reduce those environmental impacts, what conclusions you can draw, and what recommendations can be made from there. For example, look at the goal and scope for a wooden pencil versus mechanical pencil. Now, the goal here is to compare 2 writing utensils for the classroom use. Now, we can start from cradle to grave. So, lumber forest, get the lumber mill, manufacture, retailer, use, end of life. You do some sharpening, you use electricity for the sharpening. If you do mechanical sharpener, so there is something here, some material is used there as well. So this is, you get the entire process flow diagram. Similarly, for mechanical pencil, you get the entire process flow diagram from oil to polyethylene, polypropylene, and then rubber, graphite, packaging, and so on and so forth. You see T in this slide and the previous slide as well. There goes on the transportation, a lot of transportation. So function and functional unit. Function says service provided by the system, what it does. Functional unit is give the function a number value. So it allows comparison between products and the reference point. So for example, wooden pencil versus mechanical pencil, function will be what? Providing. Functional unit could be 1 meter of writing, 10 meters of writing, 100 meters of writing. So items to consider, what are the inputs, what are energy, material, labor, output, products, electricity, material, waste, emissions, co-products and all. So we have to collect data. Data, we try to collect time-sensitive data, past 5 years, geographical data, best available technology, representative data, consistent data, and also on and so forth. Never forget persistence, completeness, and all that. So when you take another example, like in terms of paper plate versus china plate. So now what is the function here? So in terms of function, it's provide the meal. To make this meals, it's basically serving the meal. Now the functional unit could be say serving 30 meals or having meals every day for a week or for a month. So that becomes your functional unit. So in this case, you will need, say for example, if you take every month and you just take lunch and dinner, so it becomes what? Your 30 days in a month, so 60 servings. So you need 60 paper plates versus one china plate, but which is washed at least 59 times. So that's what you need to so that becomes your functional unit. So based on that, you do all the calculation. Because if you compare one paper plate versus one china plate, of course the china plate will lose. But that's not a fair comparison because you are going to use that china plate again and again and again. So, but in between you have to wash them too. So and then for the paper plate, you're assuming that you're using it only once. And then after usage, you're putting it into the waste disposal stream, and where it ends up, whether it ends up with a waste to energy plants or a composting plant, that also has to be taken into consideration. So once you have all this, you look at the different environmental impact categories: global warming potential, abiotic depletion, human toxicity, eutrophication, acidification, and all those things. So you collect all that, but what is the purpose of all this data? Scientists can make recommendation of choices that are less impactful using the data. Scientists can also analyze a particular situation, particular impact, and focus on a solution. Industries are going to looking at ways to reduce their environmental footprint, especially since from January 1, 2026, European Union will have every product being sold in European Union will require to have environmental footprint declaration. So that really becomes quite, like they have to do it. There's no other options. So every company has to come up with this life cycle assessment calculation, and at the same time, they have to get it certified as well. So let's look at another example. This is a CFL bulb versus incandescent bulb. Compact. We know that CFLs are better, but how much it is better? How do you do life cycle assessment of that? Same thing, goal and scope, inventory, impact, and interpretation. So you start from resource acquisition, manufacturing, distribution, use, and end of life. So bulb, as you like glass, tungsten, copper, a lot of things goes in there. So all these resource has to be acquired. So extraction and transformation. Then once it's made, you are packaging it, transporting it for disposal. People are using it. And then there is the end of life. So if you take the entire box, the dotted line that you see in terms of the system boundary, this is known as cradle to grave. So it started from very basic raw material acquisition all the way to the end of life. But you can also, so many times the company will say that actually I don't have any control on this once it leaves my premises. So I'm manufacturing it, I'm bringing it to the distribution. But what happens during the use and end of life, I have no control. So that you can have a dot line from going like this and come back here. So that will call cradle to gate, not cradle to grave. So whenever you are looking at an LCA report, be careful in terms of how the LCA was done. That's very, very important. So bulb's function is lighting. Now, as I said earlier, LCA is an environmental accounting exercise. So you find out all the environmental impact, what kind of environmental interventions can be provided. So accounting for all environmental interventions associated with life cycle. So again, resource acquisition, manufacturing, distribution, use, end of life. You get all these input parameters: natural resource, iron ore, crude oil, water, wood, solar energy, and all that. You get the emissions out in terms of air emissions, other environmental interventions like radiation, heat, noise, and all that. And for all of these, you do it for a certain functional unit. Functional unit is the amount of function to which all inputs outputs will be related. Now, functional unit, as I tried to explain earlier, product comparisons in the functional unit or comparison basis. In many cases, one simple cannot compare product A and B as they have different performance. For example, when if you're comparing milk carton versus returnable milk bottle. Now, maybe that's returnable milk bottle can be used many, many times. So what can be compared is the two ways of packaging and delivering 1,000 liters of milk. That could be 1,000 liters of milk, packaging and delivering using method A versus method B. So that's kind of the fair comparison. So here life cycle of the light bulb. So we have the bulb function is lighting. So primary function is of course is the lighting. There is a secondary function of heating as well. The incandescent bulb creates warmth and also creating an ambience. In terms of functional unit, providing 700 lumens of electricity. That's what we have chosen as a functional unit. Why? Because that gives us 10 bulbs of incandescent versus 1 bulbs of CFL. So it becomes easy for us. So 700 lumens for 10,000 hours. So key parameters. So for incandescent bulb, that would be 1600 kilowatt hour of electricity because one bulb is 60 kilowatt hour. So 10 bulbs is 600. And CFL, it will be 14 kilowatt hour of electricity. And then you can also look at the lifetime watt versus lumen ratio. So for both of these, we have to calculate, we have to get this LCI inventory. So you need like a bulb, you need the packaging, and you need the electricity. So 700 lumens for 10,000 hours. So that requires 228 grams of glass for that bulbs, 232 grams of cardboard for the packaging, and of course, that much energy. So for in the databases what we have that we have collected, there are a standard database now available, and the database do have for all the standard unit processes. The data are available. For example, here as you can see, for 1 kg of glass, whatever is the input and output we know, and this is just a three. Three parameters have been provided for both input and output, but it has nothing. It is much longer than that. The list is much longer than that. But here for comparison purpose, only 3 items, and the three same items have been provided. So for 1 kg of glass, you need this much of crude oil, this much of iron, this much of water, this much CO2 emissions, PM 2.5 emissions, this much benzene emissions, and same thing for the cardboard and the 1 kilowatt hour of electricity. But what we need is 228 grams, we need 232 grams, and we need 600 kilowatt hour. So what we'll do is, in terms of the elementary flow, we will, for 1 kg of glass, this much, so how much for this? 1 kg cardboard, this much, for how much of this? 1 kilowatt is this much, how much for this? So you just do the unitary method, so per functional unit, and you calculate that. So this is how it is done. So you get all these inventories. And this is what is typically, because for any particular, even for a, as you saw in the earlier, in the bulb, there are so much of input parameters. Here we have just taken 3 of those. So, but there are a lot of other input parameters there too. So, but if you can, if you try to do it everything manually, it becomes too long. So we start using the softwares. And good thing is that EcoInvent database, which on EcoInvent or any database for that matter, which is available nowadays, do have these unit processes data available, which we can access to while using this software. So you have the inventories coming in because there will be hundreds of different elementary flow. We use 3 of them. Very hard to interpret sometimes because if it's more than 7, our brain cannot like process it. So we neglect the process in which contribution is less than 0.1%. So as I said earlier, there is a database, EcoInvent database, which is available as a Swiss organization. They have taken data from different sources and prepared a central database. It is available for many developing countries for free, especially for the academic purposes. And it does come with several softwares, which when you buy. And there are other databases available too. So once you have these elementary flows, what we try to put it is, okay, all these emissions coming out, so what does that mean? How it is going to impact? So we have broadly classified the impact category as per the IPCC document: global warming, ozone layer, land use, natural resources, acidification, eutrophication. So we kind of correlate the emissions coming out to these different impact categories. And after these impact categories, we try to come up with a single score, very similar to air quality index or water quality index, or say any Sensex stock exchange Sensex numbers. So that single score gives an idea whether it's a life cycle impact is on the positive side or the negative side. So it's a broadly, also it's a, although it's a simplified version, but it gives, when you talk to the regulators, you talk to the bureaucrats and others, you talk to especially like in at a top level of decision making, where people may not be aware of the nitty gritty technical details of LCA. The single score kind of methodology helps us to put the point across. So you have elementary flow, impact categories, then damage categories, then you get the final score, and then you try to look it up in terms of what you can do with this LCA. So it can be, you can designers, there is eco design, strategy development, product of declarations, life cycle costing can also be helpful. So all those things can be done. So LCA light bulbs, as we kind of already knew, that incandescent bulb will have higher environmental footprint than fluorescent, and which you see it pretty much for all the impact categories all across different scenarios. Okay, so let's move forward. So in terms of benefits, what is health as it's a quantitative method, it's a comparative, it's, you get all the environmental aspects, you get product service incorporation from cradle to grave. Gives you, also gives you global perspective. It's a complex, but you, once you have the good quality data, it's a transparent system. So it's a how deep you want to go, that depends on the goal of the study. There is a resource needs in terms of the time, money, software tools. Choices are unavoidable. Sometimes you have to make certain choices, allocations and all that. That's subjective. There are some no scientific basis sometimes as well. So, in terms of like when you try to look at recycling, but it also it helps us to avoid some of these scenarios of problem shifting. For example, if especially when you're looking at cradle to grave, recycling products that contain heavy metals, so that is again problem shifting from one place to another. So we can be in LCA, you have to kind of capture that. In exporting a hazardous waste, that also is your problem shifting. To remember, replacing zinc gutters by gutters in PVCs, to other environmental contaminant, incinerating waste that contain heavy metal instead of landfilling them, reduce acidifying emissions by increasing GSGs, spending savings from fuel efficient cars, but you're using for holiday flights. So there are change of the consumer pattern. So when you try to look at it, kind of helps us to capture the kind of big picture. So in terms of environmental preoccupation, earlier it used to be all cleanup. First, it's the end of pipe approach. You just do all the contamination, and with that would clean up. And then there was an emission reduction, like let's try to at least reduce the emissions. But nowadays it says pollution prevention, not create the pollution in the first place. All the other name is cleaner production, design for engineering, green chemistry, life cycle management, and all that. So there are several environmental assessment tools. LCA is one of them, but there are risk assessment tools, environmental impact assessment, substance flow analysis, and then all of them has a local or regional approach, as you can see on this slide, and they do cover a variety of aspects. LCA kind of, among all these, LCA is kind of the broader one, which try to capture the global and also product system, and it also has tried to capture the multiple effects. So again, but LCA is also a modeling exercise. So whenever you go for any model is as good as the data that you get for the model. So for systems definition, function, product systems, so there is an economic model, there's a technological model when you get all those impact production inventory and elementary flows. Then you have the impact assessment, which is the environmental model. So it's a amalgamation of economic, technological, and environmental model. So limits, there are limits because you are that you like assist impacts rather than potential impacts, and then you have your like it's a relative expression of impact score. So not real impacts exceeding a threshold. You have the safety margins and risk. So only environmental aspects, social and economic aspects with other tools are not there. Not all process and flows. Data quality is questionable sometimes. There is an impact assessment, like choose an impact categories, what impact categories you are taking, and all that. So for example, in early 1990s, California had a policy goal of reducing emissions of air pollution, and they wanted to adopt zero emission vehicles into 2% of the fleet. These vehicles are battery powered, lead acid batteries. These vehicles had no tailpipes. So, but the study in 1995 says that this policy would not achieve its intended goal. So, what were the problem? The problem is cars fully powered by the batteries need to be recharged. Recharging happens with electricity. Electricity production has air emissions. Battery were lead acid batteries. So, heavy batteries are a battery only power, large amounts of lead needed. So, there is a lead manufacturing and recycling emissions. More lead released than without ZEVs. So LCA could have pointed this out, but was not performed originally. History of LCA started from 1969, the Coca-Cola industry, when they were the first in the LCA, looking at the options of like a aluminum can versus glass. And then they found that actually moving to like aluminum plastic bottles. Actually, that's what they had. Like the first going for the plastic bottle, and it was a very better thing to do based on the stuff that they found out at that particular time. Then they also look at the packaging, environmental report on packaging. Then we had 1984 is when the LCA again come back in a bigger way. We had the CTAC workshop, European guidelines for equal leveling, ISO methodology came up. Then we had this life cycle initiatives, social LCA guideline, European LCA platforms. All those things came in picture. So in terms of the ISO framework, we talked about earlier, goal and scope definition, lifecycle inventory, lifecycle impact and interpretation. So goal is to find out what just is not a quick summary of different things that we just talked about. Goal is what is the object? What is the reason for doing it? Goal must clearly define the intended audience. What are the systems to be included? Functional unit, reference flow, system boundary, allocation rules. All those things kind of becomes part of the goal. Functional unit function is kind of functional unit gives us the calculation reference. Function is what is the intended use of that product, what the product is supposed to do. So need to differentiate between primary and secondary functions. So there are primary functions as well as secondary functions. Then we have the reference flows, amount of product necessary to fulfill the amount of function. So it's a what must be purchased in order to fulfill the function. So it's a different for each compared system. So product life, number of users, and all that. Unit process data and LCI. So unit process is where you get all those elementary flow coming in, flow going out, and you have unit process one, unit process two. So two types of flows. Those are so in theory, all process required to fulfill the function. So you get all this resource, you import their output, and then you for getting the function. Sometimes we look at only manufacturing and distribution, cradle to gate study, as we talked earlier. And sometimes you can also have only gate to grave study, where for example, life cycle analysis on municipal solid waste management, because everything is the same. If you want to look at the different ways of managing waste, so waste, once it's produced, you're looking at waste to disposal. You're not looking at how the product is manufactured and all those things, because whether you do product waste management using plan A versus plan B versus plan C, all the things in terms of product development use stays the same. It is once it comes to the waste disposal stream, it will be different. So we can do get to grave study as well. Defining system boundaries are also important. Sometimes depends on where you are. For example, there is a famous comparison of McDonald's and the conventional mom and pop restaurants. In McDonald's, agri-food production is if you look at the McDonald's and conventional restaurant, agri-food production is the same, transport is the same, centralized preparation in McDonald's, disposable packaging in McDonald's, cleaning reusable dishes in conventional, food cooking is done in McDonald's. In the conventional restaurant, you're also preparing and cooking. So cleaning, heating, and lighting may be the same. Food and packaging waste management will be there in McDonald's, but food waste management in conventional restaurant. So comparing one of these versus one of that will be a problematic. So there are ways we can put certain comparison which is kind of fair to both. So they provide the same function, And the intended process are those which contribute more to a fixed percentage, so total mass of input to the system and all that. So those are very, very important, like how you make the comparison. So for example, here you have a pesticide and a herbicide A versus herbicide B. They are being applied for tillage and harvest for 1 kg of wheat. Now functional unit is producing 1 kg of wheat. As long as if you want to replace this herbicide A with herbicide B, now herbicide B, if it has a different impact in terms of the yield, then you cannot, you need to take into consideration the other aspect. Say, if you're producing 1 kg of wheat, exclusion of production and application of pesticides, tillage and harvesting, if the cultivation is the same. Now, herbicide A and versus herbicide B. But in case that herbicide A yield is different with herbicide A versus herbicide B, then in that case, you need to take the entire process. Why? Because 1 kg of wheat with herbicide A needs 25% more land. Now, 25% more pesticide use, more tillage, more harvesting. So all process must be included. So this data is required. Data quality, we talked about that. Temporal data, geographical data, and all that. Primary data is the data that you collect. Secondary data is that you get from the literature. And in LCA, in short, is you have this different product system where all these different units are connected together. And for this entire system, you design, you kind of try to get the data as per its function. Individual unit processes, you have the input from technosphere, elementary flows coming out, elementary flow going out, and your product and other things. So entirely together, all these unit processes are connected together. Each one has that input and output, and overall they work towards our LCA. So inventory of elementary flow coming out, inventory of elementary flow going in for the for the functional unit that we have chosen. So in terms of LCI, goal and scope, preparing data, data collection, validation of data, relating data to functional unit, data aggregation and all that. So we do use softwares. There are several databases, Outlight, Lifecycle Assessment databases. Some are disaggregated or connected process database. Disaggregated means data available for each unit process. It's really actually better if you want to do it more detailed LCA and do even some research related to LCA. But mostly data available is for each unit process, as I said. And then there are, and then aggregated is basically data available for the entire product system. So black box represent like cradle to gate inventory. So there are, in that case, for the entire process, you have the data, but you don't have the data for individual unit process within that process, as you can see over here. So we have the data available for this entire blue box, but not for 1, 2, 3, 4, 5, 6, 7, 8, 9 unit processes are listed within it. So disaggregated is needs software for calculations. Aggregated is calculation already done. Possibility to adapt database. Disaggregated is better. Validity is also depends on the database, but can be checked. Contribution analysis you can do better. Provide to create distribution data set. So disaggregated data in general is better than aggregated. But if you are not a like a expert LCA practitioner, aggregated data kind of help you to start with. So there are different available process database available, which is can be used, and some are cost, some does cost, some are available for free. So, and once you have the data, you can do these kind of calculations. Where, for example, energy 1 kilowatt hour of electricity for different countries. These are the transport CO2 fossil fuels for different materials. So this is how the inventory data is available in this databases. So for the interest involved, say if you're using all those inventory data, you can calculate how much is glass, copper, cardboard, and all that. Transportation, use, electricity, you find out this is per functional unit. Then per unit, CO2 is coming out per unit, how much will be required. And then you per functional unit, you compare with to the functional unit, and then you get total 14.5 CO2 kg per functional unit. Then we already kind of talked about impact assessment methods. So there are different global warming, GHG emission, and infrared reinforcing. These are the different impact assessment methods. And then when you take this in midpoint and endpoint, and then you try to compare with them together, you can put it in different categories. So global warming, 1 kg CO2, 25 kg, so 1 kg methane is 25 kg CO2, N2O is your total 298 kg CO2. So that's you develop all this characterization model developed by the IPCC and other organizations used to calculate And then you need how much years they will be available. So typically we do it for 100 years. So this is your lifetime radiative efficiency, radiative efficiencies and direct exposure numbers that is coming out for different for the different emissions. So chemical formula, how much lifetime years, radiative forcing efficiency. Usually we go for 100 years and we use that. So you can calculate, again, you can get all these numbers. So greenhouse gas potential for incandescent bulb. So you get carbon dioxide for this, and you know the conversion factors, and then you calculate the greenhouse gas emissions. So total is 23.2 kg CO2 per functional unit. Then you try to normalize in terms of I'll say related to the functional unit, and then you come up with your single score at the end. You do some weighting and characterization. So these are all typically will be done using a software. It helps you to do that. Of course, you have to put your input. So you have all this elementary flow. You do this classification, then you do normalization, then you weighting and aggregation, and finally you get a single score. So I think that's pretty much it for this particular video. And there are some other examples which is given as part of the PDF, which you can look it up. So thank you. And I hope this was useful to you. And we will be looking at some more modules later on. So thank you very much.